All right, tonight we're going to be talking about ionic bonds and covalent bonds. And before we start that, we got to talk about what is a bond and what is bond formation. Well, I want you to think about a bond in terms of magnets. When two magnets come together, there's an attraction, and you can see it right here down at the bottom of the page. The north pole of the magnet and the south pole of the magnet slam into each other and they get a pop. That's energy being released. And when that happens, it becomes much more stable. So therefore, bond formation is exothermic, all right, and it stabilizes the elements. Now let's take a look at the flip side, and we're going to talk about breaking of bonds, which if you look over here, you see these guys pulling the magnets apart. It's tough. They're struggling to get that magnet apart. And therefore, to break these bonds, it's endothermic. Energy is absorbed, okay? So it's really tough. So now what I'd like you to do is I'd like you to take a look at question number 1. Question number 1 says, which statement is true about the equation below? So what do you think the answer might be for that? You have an NaCl molecule breaking apart to an Na plus a Cl2 molecule. I'll give you 3 seconds. All right, here. Well, we see a bond between the sodium and chlorine atom are broken, so you can automatically cross out 1 and 2. And we know to break something, it has to absorb energy. So therefore, it's going to be choice number 4. But why, in fact, do bonds form? Well, reality is this. All atoms want to have a full outer shell, which is 8 electrons, which is what we learned in our last unit. Therefore, your group 18 atoms, as we know, are the most stable. We call them noble gases. Bond is formed when the element's valence electrons from one atom are attracted to another element's nucleus. Here's a look at the sodium and the chlorine atom right below. Here you have sodium. If we look, we see we have a 281 electron configuration. We have chlorine, which is a 287 electron configuration. Now, what in fact happens is the sodium is a metal, and we learned that metals are the biggest losers. Why? Because they lose their valence electron to the nonmetals. But in fact, why does that happen? Well, if you look over here, so metals have fewer valence electrons. It's like cinder blocks. If I have 8 cinder blocks, I got to put them together, and I have 7 over here by the chlorine, I have 1 here by the sodium. It's easier for me to take the 1 and bring it over to the 7 instead of the 7 and bringing it over to the 1. So then why are metals considered the biggest losers? Because they lose their valence electrons in bonding. They are the biggest losers. They lose their electrons. Now that we understand that, let's talk about types of bonds. And the first kind of bond we're going to talk about now is going to be an ionic bond. Now we know that ionic bonds are a bond between a metal and a nonmetal, and let's quickly review. Here I have my staircase, and on the left side of the staircase I have my metals. On the right side of my staircase I have my nonmetals. And a bond between a metal and nonmetal is called ionic. Characteristics that you must know, memorize. They have a high melting point. They have a hard crystalline structure. They're good conductors of electricity only in the liquid or aqueous phase, but they are very poor in the solid phase. And as synonym, you must know electrons are transferred with ionic bonds. So therefore, when you hear ionic, you better be thinking electrons are transferred. And again, we know what happens. Metals are the biggest losers. Therefore, the metals lose the electrons. The nonmetals will gain the electrons. Now, we have to talk about electronegativity difference. And that's where we subtract the electronegativity of one atom from another atom. And I just quickly want to give you a little insight. Look, the higher the electronegativity, the more ionic the compound. Therefore, the following is true. The bond is strong, has a high melting point, and there is a strong intermolecular force of attraction. All right, now how do we calculate the electronegativity difference, or the END? Well, we know that the electronegativity for each atom is found on reference table S. So we look for those two, and we take the large electronegativity minus the small electronegativity, which will give us our electronegativity difference. So here, let's take a look at table S. I cut this little snippet out, and we'll look at NaF. Well, heck, Na has an electronegativity of 0.9, and fluorine is 4.0. So we take 4.0 minus 0.9, we get 3.1. We could do CO2. Now the trick is there's only one oxygen we're interested in. We're not going to do 2. We're not going to double 3.5. So we take 3.5, which is oxygen, which you see right here, and you see 2.6 for the carbon right there, and you get a 0.9. Sorry about that. So, with that said, we can do questions 2 through 6, and then do questions 7, 8, and 9. While you're thinking about that, I'd like you to do that later on. I want to introduce you to another type of bond, and that is covalent bonding. Covalent bonding is really a bond between two nonmetals, so everything on the left-hand side of the periodic table. Unlike ionic bonds, they are totally poor conductors of electricity. We consider them soft. They have a low melting point, and the key difference is covalent bonds, electrons are shared. Molecular is also considered covalent. So again, molecular, covalent, shared, ionic, transferred. Now there are two types of covalent bonds. There's a polar covalent bond and a nonpolar covalent bond. I want you to think about this in terms of poles of the Earth. We know that the poles of the Earth are positive or negative. They're different. Polar actually means different. So when we talk about a polar covalent bond, what we're talking about is two different nonmetals. You can see the arrow right here. And therefore, since they're different, the electrons are shared unequally. Whereas a nonpolar covalent bond, it's a bond between two of the same nonmetals, like O2, N2, Cl2. We consider those diatomic elements. They travel in pairs, and since they're each bringing the same number of valence electrons to the party, the electrons have to be shared equally. Now, you have a bunch of questions that I'd like you to do. 10 to 13, 14, 15, 16, 17, and 18, and of course, 19 and 20. And then I'm going to talk about monoatomic elements. Monoatomic elements are elements that don't bond with anybody. We know that to be the noble gases. We also have to talk about the diatomic elements. Your diatomic elements are elements that travel in pairs. Therefore, they're written as O2, N2, I2. I think of the diatomic elements as one of my professors, Dr. Brinkelhoff. B-R-I-N-C-L-H-O-F. Brinkelhoff. Well, not really, but what it comes down to is your bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Brinkelhoff. They're all diatomic. Okay, that's our lesson for tonight. Do the questions 1 through 20, and we'll call it a night. Bye.